All right, so we're just going to do a real quick little lesson today, basically. Talk about factoring imaginary numbers, which sounds really weird, but it's actually not bad because we're only going to look at one type. We're going to look at what's called a sum of squares. And a sum of squares is when you have a square plus another square. Sometimes they're two variables, sometimes they're a variable and a number. You get different combinations. The rule is, though, and you really do just want to know this as a rule. It's so much easier. And we'll talk about why it works, but if you understand it as a rule, you'll be able to do these in seconds. So the rule is if you have a sum of squares, it's always going to factor to whatever the roots of these are. So like the root of this would just be x, the root of that would be y, because x times x is x squared, y times y is y squared. So they're going to factor to the two roots, but they have to be, the second part has to be imaginary. So it's going to look like this. Now this probably looks weird without numbers on there, but that's going to be the format that every one of these is going to follow. And the reason it works, I'll show you on this one, and then we'll look at it later on. But if we look at how this works, if you distribute it, you get x squared, you get a minus xyi. Here you're going to get a plus xyi, so those are opposites. And here you're going to get minus y squared I squared. So these two middle parts drop out, kind of like these conjugates we've talked about before. And then if this is -1, the negative times the negative changes this to plus. And so this does just give you x squared plus y squared. So that's why it works. To be honest, once you know the rule, these get very, very simple to do. So I'll show you what I mean. All right, so we go to factor, and we see that we have something squared plus something. Now, right now, these are not perfect squares. But remember, your first step in all factoring is pull out a GCF. If you divide a 3 out of this, you're going to notice it turns into a sum of squares problem. Right? So we pull a 3 out of both of those, and now we have 4x squared plus 1. These are both perfect squares, because that's 2 times 2, and that's 1 times 1. So now this is actually just going to factor, according to our rule, the root of each part of these. So it's going to be 2x, because 2x times 2x will give you 4x squared, and then 1i. And then this one's going to be the conjugate of that, 2x minus 1i. And that's going to be our factored form. And you could check this like the previous example if you want to. But again, once you notice that the two roots are just going to be the conjugates of each other, they're going to be the conjugates of the roots of these numbers, you're going to notice these go quick. So we'll look at a couple more. Again, that's 2x times 2x, that's 5 times 5. So 2x plus 5i and 2x minus 5i. That's going to be the conjugate pair. These will always come in conjugate pairs. If you want to write that as a note. So sum of squares, look for a conjugate pair. That's really the main key there. Okay, here's another one. If you notice right away, these are not perfect squares. Like nothing times itself gives me 8, which is a really dead indicator that it's going to have a GCF, just like this problem. So I believe I can take a 2 out of those. Would leave me with 4y squared plus 9. Now we're like, okay, sweet. This is 2 times 2. This is 3 times 3. So we got our 2 out front. This is going to be 2y plus 3i and 2y minus 3i, the conjugate pair. So that's the factoring concept of sum of squares. Right below this is doing that same skill, but to solve the problem. So if you remember this back from 2-3, now that we're solving, we want to actually just give the answer, the solutions to these. So again, we're going to factor it. So this is going to be just like 1x times 1x. This is going to be 2 times 2. So x plus 2i and x minus 2i is what that's going to factor to using our sum of squares rule. And then, since we're trying to solve it, we're trying to say what makes this equal 0. We just look here and we say what would make this part equal 0 and what would make this part equal 0. So we've done this before. To make this equal 0, you'd have to have 2i. To make this equal 0, you'd have to have a negative 2i. So you're going to get imaginary solutions, which actually completely makes sense. Just to show you the same thing graphically. Now, you don't have to do this. It's just a kind of conceptual understanding thing. Let me get these out of here. If I put this in my calculator, x squared plus 4, and I asked you when does that graph equal 0, if you graph this, x squared plus 4 is here. Here's our 0 line. And you're like, when does that equal 0? You'd be like, it never does. And the reason is because it has two imaginary solutions. That's why you get these answers. When you look at this graphically, you'd say it has no real solutions. It can, of course, have two imaginary solutions. That's been kind of the big concept of this section. Okay, the last couple here, more of the same. All these are saying find the values that will solve it. So we're going to factor. So take the roots of these. This will be x plus 7i, x minus 7i, equal to 0. So solutions would then be, what's going to make this part equal 0? That's a negative 7i. What's going to make this equal 0? Positive 7i. And you notice these usually are going to come in pairs like this, opposite pairs, positive and negative of the same imaginary solution. One more here. Let's see. That's 3 times 3. That's 5 times 5. So we're good to go. So 3x plus 5i, 3x minus 5i is the conjugate pair. And yeah, we're looking good. Now, what's the solution to this? If you a lot of people have trouble here. The best move is to use the shortcut that we learned back with factoring, which is always the opposite of this divided by the coefficient. So it's going to be negative 5i over 3. This one's going to be the opposite of this, so 5i over 3. That shortcut always works. If for some reason you don't like shortcuts, maybe you don't. The other way to do this is to just take the part, set it equal to 0, and solve for x. So if you solve this for x, you'd be like, all right, let's subtract that over. So now I got 3x equals negative 5i. Divide both sides by 3. So x equals negative 5i over 3. That'll work. It always works like that, which is why the shortcut's real nice. And again, it's just the opposite of this value over the coefficient. Opposite of this value over the coefficient. So that's it. So the assignment today is going to be pretty short. It's going to be just factoring and solving sum of squares problems. So keeping it real, chill today on the transition day, and then we'll kind of get back to a normal sort of grind Thursday, Friday.